you guys ready for some mathematical fun? This is going to be such an interesting conversation. You're going to be so happy with this conversation. Not going to be boring at all. Okay, the small number problem. Okay, let's think of like prime numbers, right? What are prime numbers? We got 2, 3, 5, 7, 11, 13, 17, 19, right? It seems like there's a pattern in there because they're all jumbled in. It seems like the numbers ending in 1 and 3 and the numbers ending in 5 or 7 and 9 always seem to be prime. But are they really? Because you keep stretching that out, and even though all prime numbers after 11 only end in 1, 3, 7, or 9, that's just because of our base 10 system, right? In a base 12 system, your prime numbers would end in 5 and 7, and maybe 11. But there's a lot of strange things that only appear because it's base 10. And once you get into big enough prime numbers, then there's different patterns that emerge, like prime pairs. So there's a lot of times, even with numbers with like 20 to 30 digits long, where a number ending in a 1 and then the number ending in a 3, 2 larger than it, are both prime. So you get these weird pairings of primes. But you keep stretching out because you have to keep in mind, what is a number? A number is a finite list of digits. And if you think about the concept of infinity, most numbers are infinitely long, right? So if I took this pencil and I broke it in half, I have like a 1 in infinity chance of it being a finite fraction exactly of a break. Like to get actually at a half is virtually impossible. And the almost guaranteed situation is when I break this in half, it'll be an infinitely long number percentage of the pencil left. It's not going to be a third. It's not going to be, 29/67ths. It's going to be an infinitely long decimal place fraction. So most numbers are infinite in size, which means we can't even evaluate them because they're infinite in size. And that is to say that with most numbers being infinite, any number we evaluate is relatively small, right? A 20-digit number is huge, but compared to an infinitely long number, it's infinitesimally close to 0, right? So if you have 0 on a scale and you have infinity over here, a 20-digit number isn't like sticking out here somewhere. It's right next to 0. And so is a 1,000-digit long number and a 200 million-digit long number. They're all infinitesimally close to 0 on the scale of infinity. So whenever we see these patterns in numbers, especially in statistics, you're dealing with very small numbers relative to universal mathematics. So I just wanted to keep that in mind. Whenever you have a small number, you're going to see patterns that aren't real just because you're using a significantly smaller pool of numbers than our actual numbers. You know what I'm talking about? Does that make sense? Well, we all make sense of that. And there's a lot more we can go into, but I'll save that for another time.